Now that we've talked about all of the physiological changes that go on within a germinating seed, we need to talk about some environmental factors that can affect whether or not a seed remains dormant. And the first on the list goes hand in hand with what we were talking about with the metabolic processes of seed germination, and that is water. Since imbibition of water is the first step in the germination process, water must be present for seeds to germinate. And the rule of thumb is that the harder the seed coat, the thicker the seed coat, the more water is going to be required for that seed to germinate. So we'll say the greater the seed coat, or we could say thicker the seed coat, the more amount of water is going to be necessary, because it may take not just one swelling full of water event, it might take several in order to crack that outer seed coat. Temperature plays a big factor in that, as we have noted before, and especially in chemistry class, if you're also in that class, enzyme reactions are highly temperature dependent. And so if the temperature affects the rates of, let's say, enzyme reactions, it stands to reason that all of that enzymatic breakdown of starches and fats and oils into usable sugars like sucrose and glucose is going to depend on their enzymes functioning within the proper temperature range. And so this can be highly dependent on species, as it says in your notes. Some species intentionally germinate in the cooler months of the year, others intentionally germinate in the summer months of the year. And so for every species, there's going to be a maximum, minimum, in other words, an optimum range, optimum T range or temperature range for germination to occur. Next on the list is oxygen. Oxygen, as you know, is required for respiration. The respiration going on in a seed is indeed aerobic respiration, which means by definition it requires oxygen. And as we said in the last video, respiration has to occur for the conversion of starches to sugars. So let's say sugar production from starch requires respiration to be happening. And indeed, if we look back in the notes, that is one of the events that we listed. Was there's an increase, generally speaking, in respiration in the embryo. And one of the more interesting environmental factors is light. And light, as a requirement for germination, is typically very species dependent. In many species, the embryo may remain dormant until light is encountered. And the general rule of thumb is that the smaller the seed, or small, let's say, seeded plants, are often light dependent for germination, let's say. Meaning that unless that seed is exposed to light, it will not germinate, even if the temperatures are optimum, even if there is optimal moisture in the soil and the seed is viable. In other words, it will remain dormant until it comes into contact with some light. And there's a very good reason for this being a property of small seeded plants. And a little drawing here can help illustrate this. If we were to compare, let's see, this will be our soil surface. If we were to compare two seeds, and let's say this seed, I'll do my best drawing of the seed of corn, for example, and then over here, relatively sized, very small like this, I'll use lettuce as the other example. Now, in this soil, if there's optimum temperature for both of these seeds to germinate and there's optimal moisture for both of these seeds to germinate, they may indeed germinate. And so when they do germinate, each one is going to start producing, green might not have been the best color to draw roots, but they're going to start producing a shoot and a root meristem, and they'll be growing in the proper direction. Okay? Or directions, since we're referring to roots and shoots. Now, the name of the game for a developing seedling is it has to get those shoots up above the soil so that the photosynthetic leaves can start making sugars. Because until it does, this seed's entire development of a root system, okay, and a leaf to photosynthesize with, or leaves in the case of a dicot, is totally dependent on in the case of corn, lots of starch stored in the endosperm of that seed. Now that starch, as we've said many times already, gets broken down into sucrose and then glucose to fuel all the respiration involved with the growth of this seedling. So, corn being a relatively large seed, if we planted it, let's say this was a depth of 1 inch, corn usually won't have too bad of a time getting to the surface and growing photosynthetic leaves before it runs out of carbohydrate reserves. But what about lettuce? Lettuce is a much smaller seed, and so in other words, it can't store, let's say, as much, and by size, we're talking hundreds, maybe even 1,000 times less volume than the average corn seed when compared to a lettuce seed. It can't store as much CHO, carbohydrates, as corn, not nearly as much. And so it's not going to be able to grow a shoot as long or a root as long as this corn seedling before it has to have light to photosynthesize to make more carbohydrates. And so if this lettuce seed were to just germinate being an inch deep in the soil, it's going to run out of gas, so to speak. We can use the comparison of cars. If somebody had to drive from Jacksonville to Miami and you gave them one vehicle and it had, I don't know, 100-gallon gas tank, and you gave someone else a vehicle that only had a 5-gallon gas tank in it, who would you bet on? Well, you'd bet on the larger capacity in terms of fuel vehicle to get to Miami. It's quite a ways from Jacksonville. Same thing holds true for a large seed planted below the soil surface. The larger the seed, the greater the carbohydrate reserve, and the deeper that seed can germinate and still be able to survive. Lettuce, again, being much, much smaller in size, can't afford to try and germinate down here, and so it doesn't. And the way it doesn't is it will not germinate until that seed comes into contact with light. So what I've drawn here doesn't even happen. For a lettuce seed to successfully germinate, it needs to be right at the surface where it can be exposed to light and where it has, let's say a 1/16 of an inch or maybe even less to grow before it can come up. Let me use green here and start putting out its photosynthetic leaves, by which point it will have exhausted its stored carbohydrates, but it can make its own carbohydrates now via photosynthesis. And so this is why it's not uncommon for a small seed to be light dependent for germination. You can see examples of this all the time. If you look in agricultural areas at fields that have recently been disked under or plowed under, and for the first couple of days, the fields look nice and clean. There's no green plants growing on them whatsoever. But after one rain, or maybe even just a couple of mornings with heavy dew, you start to see little patches of green popping up here and there. And after a couple of weeks, if nothing's done with that field, it'll be almost solid green with weeds. And those weeds did not just fall out of the clear blue sky, and birds didn't poop them, or wind didn't carry most of them, and suddenly billions of seeds landed on this field. What's going on there is those seeds had been in the soil all along, and by plowing that soil, some of those seeds were exposed to light and they start to grow. And many of our most common weeds happen to be light dependent for germination, and some of them can stay in the soil for decades before they germinate. So that's just an example that you might notice while you're out and about of light dependent seed germination.